Welcome back, ladies and gentlemen, for the last recorded video that I'm doing. This one is matrix operations. This is section 6.3 in your book. And I have copied the bulk of this directly from the book. So the book has links to videos you can watch if you want. If you're in my second class at 3:30, Ms. Dalrymple already posted some notes. You don't have to watch both sets. But if matrix multiplication is a confusing mess, I highly recommend shooting over to that video and taking a look at it, because I have a slightly different way to write it that may help. But we have to move through the rest of this first. So the first thing we have is what's called the order of a matrix. So this is read as an M by N matrix, and it is always, M is always rows, and then N is always columns. So matrices are written and are referenced rows, then columns. And then when we're going to do multiplication later, it's always rows, columns. So you want to remember the words in that order. I like to even write it down. Rows by columns. Wow. Okay. Now, the book squeezed this in the explanation of a practice problem rather than making it its own special line. Very rude. So we have 3 extra phrases. A square matrix is a matrix that is square, meaning it has the same number of rows and columns. So a 1 by 1, which is literally one number, would technically be a square matrix. We usually don't talk about matrices that small though, because it's a number. It's not really a matrix. A row matrix is a matrix that only has one row. So it'd be a 1 by something. Some n. And then a column matrix is a matrix that is only one column. So it would be some m by 1. Now, if you were going to do any sort of computer programming, especially graphic computer programming, understanding how matrices work, how the matrices multiply, and making sure that you have your dimensions straight for that can be useful. Not so much the nitty-gritty, like being able to do it by hand, but understanding what has to happen for the multiplication to work out. Because matrices can actually represent like a vector, a movement in space, especially when somebody's doing like a really weird movement where they're not just going straight, they're going like off at an angle. You can actually represent that with a matrix and then apply it as a thing that moves whatever object in the direction desired. So this is where the math comes into play for programming video games. All right, so the first is order of the matrix, rows by columns. So our first one here, we have, let's use some highlighters. So that is 2 rows by 1, 2, 3 columns. So it is a 2 by 3 matrix. That is the order of the matrix, 2 by 3. Now our next one here, we're going to count rows, and it seems a little silly because it's single numbers, but still, if I was typing this on an Excel spreadsheet, each of those would get its own row. So that is 4 rows. And then my number of columns is just 1. So that is a 4 by 1 matrix. And since it is just one column, we would indeed identify that as a column matrix. One of the questions on the homework does ask you to use those phrases. So if you skip down to D, there's the row matrix. one row and 1, 2, 3. It's a 1 by 3 matrix. Now, the one I skipped over, C here, count it out. 1, 2, 3, 1, 2, 3. It is a 3 by 3. And oh, look, those numbers are the same, making this one a square matrix. Now, this particular square matrix also is a very special square matrix. This square matrix and other square matrices that have the same format where it's a diagonal of ones, everything else is zeros, ends up being what's called the identity matrix, the multiplicative identity matrix. If I multiply that to a matrix that has the appropriate rows or columns, I will get the matrix that I started with back out. So we can actually use that to our advantage later on when you're finding inverses. That's you have the matrix, you put the identity matrix, then you row reduce it. Yep, that's where it comes into play. So what we're talking about here mostly is just notational things. So sometimes when we have a big giant matrix, we want to be able to reference a particular item. And in programming, there's a number of ways to call that. In math, though, we just use this little notation here where we have A with a subscript. So the brackets around it means it is the matrix of all A elements that are I is the row, J is the column entry. It's always row column. So like here, A43, that's not 43, it's 4, 3. Really huge matrices actually have to put a comma between the numbers. So that is the element that is in the 4th row and the 3rd column. So it's always row by column. So let's take a look at A down here, and then we've got 3 different entries to pull out. So I see we have 3 rows, 1, 2, 3, 4 columns. So this is a 3 by 4 matrix. Doesn't hurt to identify the order. Not square. Does kind of look like an augmented matrix. All right, but we're just pulling out entries. So what is the A23 entry? 2nd row, 3rd column. All right, so 2nd row, 3rd column. That is actually a 0. All right, but check it out. B, A32, not the same thing. So 3rd row, 2nd column is 8. This means if you are dysnumeric, if you swap your numbers, you have to be really careful on these, like double, triple check what pair you're finding and where you're going in the matrix for this. Now, on most finals, we don't do a lot of these. So if you have to pick something to study, study something else. And then our last one, 3rd row, 4th column. 3rd row, 1, 2, 3, 4th column, the lovely -9. So 0 is a number, perfectly fine to have 0 as an entry. You look in there, square root of 2, that is a real number. -pi, still a real number. A matrix just has to be made up of real numbers. Now in crazy later math, you could even have complex numbers in there, but we're not going to do that. All right, so that is how we're going to talk about matrices. The order, the size of the matrix, and then individual elements are called by the row and then the column numbers. Now we can add and subtract matrices. But first, the book wanted to put forward this idea of equality. When are 2 matrices equal? In order for 2 matrices to be equal, all of the entries have to be exactly the same. So I can't have one number in one spot and a different number in a different spot. All of them have to match perfectly. So If this crazy matrix equals this crazy matrix, then each entry, first row, first column, has to be the same. First row, second column, y has to be -4 if these are equal. And then second row, first column, x is 9. Second row, second column, z must be 7. In order for those two matrices to be equal, those all have to hold true. Now, for most of those, it was a variable on one side, a number on the other side, so it just defines itself quite nicely. But the first pair, the 3 and the 3, if those weren't the same, they're not equal. The rest of them, I'm just setting it equal, working it out. But here, this isn't about, oh, can I divide everything by a number or multiply everything by a number? Straight up, are they the same? Exactly the same. All right, now addition and subtraction, we do this element by element. So first row, first column plus first row, first column. First row, second column by first row, second column. So it's literally just like a matching each of the entries and just adding the numbers, whatever they tell you to do, entry by entry. That's how addition and subtraction will work. Not how foo-foo multiplication will work, though. We're going to have scalar and then the big stuff. All right. I'm going to cut this and then I'll come back and do it.